Hello, welcome to this presentation of International Plumbing Code. My name is Thomas, and in this presentation we're focusing in on Chapter 6. Chapter 6 is all about water supply and distribution. Now think about, what are the two most important functions that a plumber fulfills? Well, a plumber brings clean potable water into a usable space, and then a plumber removes waste and wastewater from that location. We have water pipes that bring it in. We have drains and waste lines that bring it away. That's basically what we do. That's it. I mean, the rest of all the parts and fittings and stuff that we build are to accomplish those two very basic goals. Okay, that said, this chapter is one of the very important chapters in all of plumbing, right? Because we're looking at that first portion of bringing water and making sure that it's safe. Now, if we look at planet Earth, it's maybe 70% covered with ocean water. Seems like there's plenty of it around. But you and I know the reality that while we have to have water to live, as everything on planet Earth has to have water to live, it has to be good water. And when I say good water, that means it's free from contamination, pollution, or in other words, it's water that won't hurt us. Contaminated water can kill us. So even though we can't live more than a couple days without water, we could die in a day if we get contaminated water. And for this reason, there's a major chunk of this chapter that focuses on protection, particularly backflow protection. We're going to have an entire presentation just on that because it's so big and so important to maintaining sanitary life. But in the meantime, let's dig into Chapter 6. We're going to look over water supply and distribution. That's talking a lot about pipes, controls, and things that go into providing potable water. The first section in International Plumbing Code Chapter 6 is 601, General. And we start with 601.1, where it talks about the scope. Now, scope is just talking about, what is this all about? What does this include? Let's see if we can summarize this entire chapter in a sentence. And here it is. This chapter shall govern the materials, design, and installation of water supply systems, both hot and cold, for utilization in connection with human occupancy and habitation, and shall govern the installation of individual water supply systems. So that kind of covers it. Anything that deals with bringing water to human occupancy and our personal space, that's what this is all about. In 601.2, it talks about solar energy utilization. The idea here being, if we want to heat the water, why don't we use the sun? Well, that works some of the time, and obviously not some of the time. But regardless, if you have a solar heating system for your potable water, that's one thing. But if the solar collector is connected to non-potable or an indirect connection, closed loop as we see here, that solar panel is going to be transferring heat into a heat exchanger. In this case, we have a tank serving as a heat exchanger. And that heat's just going to transfer into the water, but there's no actual connection between the two. In that case, it says the use of solar energy shall not compromise the requirements for cross-connection or protection of the potable water supply system required by this code. Let's say you live in a place that's cold and it might freeze at times. You can have regular water running through that solar collector. It will freeze. So you put in some glycol. But obviously you don't want glycol in your potable. So the importance here is on keeping the water clean and not having any connection between the two. In 601.3, it talks about existing piping used for grounding. We're referring to electrical grounding. Now, think back in time. The earlier plumbing supply and distribution piping was all galvanized steel. Galvanized steel is very electrically conductive. And then as time went on, we're talking like into the 70s, 80s, 90s, during this period we had copper water service pipes coming into the building. Copper is also very electrically conductive. And for that reason, many electricians have grounded their systems to the water pipe. They just hook that electrical system ground right up to our water pipes. That grounds out the electrical just fine. But in more recent years, we have gone to plastic pipes, which means there's not a lot of conductivity in that pipe material for electricity. So let's say we're replacing a water service pipe coming into a building, and we remove the metal and we remove the ground, and we go and connect a blue plastic poly pipe right up to the underside of that, and we have then lost that ground connection. That can cause fires. That can cause electrical issues. So 601.3 says metal shall not be replaced until approved grounding is provided. Now, as a plumber, does that mean you have to go and figure out what it means to ground electricity? I personally wouldn't. I've been in this situation many times in my plumbing career. I would much rather call a professional and say, hey, you know what, let's get an electrician in here. They know how to properly ground, and let them do that. Make sure that it's done properly. 601.4 talks about tests. We're talking about testing this piping system that we have installed. And in regard to tests, the code says, hey, we already talked about this back in section 312.5. So if you want to know how to test your water distribution system in a building, just head back to chapter 3 and you'll find it there. 601.5 talks about rehabilitation of piping systems. I mentioned old pipe, galvanized in particular. The inside of that gets very rusty and wears out. I've seen it where it actually pinhole leaks and comes right out the side because it's so corroded. In systems that are like that, and I might pause and say, hello America, we've had galvanized piping systems for 70 years now. These pipes are going to likely start giving up in the future. We've got to have some options. What are your options? You either cut it out and repipe the whole house with PEX or whatever, modern piping, or there is this rehabilitation option. The process involves sandblasting the inside of the pipe, clearing out the rust, and then lining that with epoxy. It flows through, it coats from the inside. You basically create a new pipe inside the pipe, and it works. It saves the trouble of tearing open walls and ceilings if you have to pull out the pipe, or if you're just running a new system next to the old system. So it's a great option, and as long as we comply with the ASTM 2831 standard, which is just telling like the standard for installation, then it is approved. It's an option. 602.3 talks about individual water supply. What this is referring to is a well system, a private source for acquiring potable water. Anywhere that a building could be connected to a public or culinary water system, that's what should happen, right? We can supply from the community. But if that's not an option, you're out in the country and you need some water, well, you dig a hole and pull it out of the ground. There are a number of requirements in here in 602.3, including a description of sources for where you can get that water, different well types, minimum quantities and water quality, the disinfection of the system and pumps involved. I'm not going to go into a lot of detail here because in Utah, our amendments have deleted this entire section. This section has been replaced by our Clean Water Act, which details out how we handle wells and private water supply. We're going to move on to 603, but before we do, I need to review some terminology with you. What is the difference between a water main, a water service, and a water distribution pipe? These are terms that are used throughout this chapter, and we kind of need to understand that. But for code purposes, let me just explain that the water main would be the public water supply pipe, the big thing out in the street. That's the main. Now, a lot of times as we're just, talking about pipe and bringing water into a building, we may refer to the pipe from that main into the building as the main water pipe. Well, it is like the main thing coming into the building, but by code definitions, that is called the water service pipe, to differentiate between the main and the street and the pipe that's coming into the building. So that is our water service. From there, once the water gets inside the building, then we have distribution pipes. It branches all over the place and delivers water to fixtures. So that's the three different definitions. Hopefully that helps you as we talk about these to understand which ones are which. All right, now that we're clear on what a water service pipe is, let's look at 603, water service. 603.1 gives us the size of the water service pipe. Now this is the minimum. The smallest you can have for a water service pipe is 3/4 inch. Well, back in the galvanized days, they'd run in some 1/2 inch pipe, and then they'd run 1/2 inch to all the fixtures, and it was all the same. But now, we have a minimum of 3/4 inch, and from there we also have water sizing tables. Depending on the load on the other end, as we distribute that water, we may need something bigger. But the smallest you can go would be 3/4. Now we'll get into water pipe sizing later on in another presentation, because that goes right along with what's happening here in chapter 6. But for now, just be aware, 3/4 inch minimum. Now 603.2 requires a little bit of explanation. It says separation of water service and building sewer. As we talked about before, plumber's purpose is to bring clean potable water and to remove waste. You don't want those getting mixed, right? And for that reason, we want to make sure that our water service pipe is far from anywhere near our building sewer. But many times, we may be running a trench and it's pretty convenient to just put them in together. So here's what it has to say about that. Where water service piping is located in the same trench with the building sewer, such a sewer shall be constructed of materials listed on table 702.2. Chapter 7 is coming up later. 702.2 tells us what type of material we can use for a building sewer. As long as we're using the materials on that table, we can put them in the same trench. But if we are not, and what I'm talking about is the stuff that we used to use. Back decades ago, there was a pipe called Orangeburg. It's kind of like a thick tar paper. It's not really rigid. Many of them are being replaced today because they smash an oval and they get roots in them. And this is not the kind of pipe that you'd want to have your service in the same trench with. So again, we just check the list, and anything nowadays, I mean like PVC, cast iron, whatever else you'd use for your building drain or building sewer, most of the stuff we can get is on that list, and we can put our pipes together in the same trench. But if they're not, here's the rule. You would need to separate them by 5 feet of horizontal distance, so separate trenches. Or if they're in the same trench, the water service would have to be 12 inches above the building sewer. That also applies if the water service is passing perpendicular across the top of the building sewer. You would need to have a 12-inch minimum over the top of that. 603.2.1 makes another important point about the water service pipe, and that is that it should not be anywhere near sources of pollution. Those pollution sources may include cesspools, septic tank drain fields, or seepage pits, or if there's contaminated soil. Any of these things that could contaminate that service pipe and the water coming through it, we would need to seriously avoid. All right, we've talked about the water service pipe. That's the pipe bringing water from the main into the building. Let's talk about distribution now. 604 goes over the design of building water distribution systems. There's a lot involved with design. There's different methods that we use to distribute that water throughout the building. And this is going to go over what's approved and what are the requirements for that. And along with that, we also have sizing. So 604.1, as I mentioned before, the sizing of pipe is an important thing. But interesting, in the International Plumbing Code, they've removed all sizing methods from Chapter 6. Some other codes may have sizing methods in that same chapter talking about water, but they've removed it. And what they say is that it has to conform to accepted engineering practice. Methods utilized to determine pipe sizes shall be approved. Maybe that just means whatever you're going to do, just as long as it meets what the inspector expects. Fine. But they do give us in the back of this book the appendix, which goes over how you can size pipes. There's several methods. And that's why, again, we're going to go over that in a separate presentation because it takes a minute to go over that. But in general, it has to be sized correctly and the sizing has to be approved. 604.2 talks about system interconnection, and it says at points of interconnection between the hot and cold water supply piping systems and the individual fixtures, appliances, or devices, provisions shall be made to prevent flow between such piping. We are specifically talking about not crossing hot and cold. Obviously, if you're running pipe and you accidentally hook pipes up to the wrong side, like, oops, this hot connected to the cold, you're going to have issues. Water will always take the shortest path, and it's going to travel through. So you may have hot in the wrong place at a fixture or cold in the wrong place when you want hot. So we prevent the flow between them. This was okay back when we had two-handle faucets and valves. I mean, aside from crossing pipe, you just have your hot or your cold, and it's one or the other, and you can mix it if you like. But over time, faucet and fixture designers came up with single-handle faucets that function for both hot and cold. So we're mixing them. We're bringing them together at a point. And what you cannot have when those pipes come together is the ability for hot or cold to cross over one to the other. Let me give you a classic example. Moen. The Moen Troll single-handle faucets that have been installed and used for decades had a single handle, a single cartridge inside of there, and it would control hot and cold. That was fine for a long time, but as they wear out, particularly the older brass cartridges, they allow for crossover. I've helped many customers who've had problems either not getting hot water where they want or getting cold where it shouldn't be and running into all kinds of issues. And once we take out that cartridge and replace it with a newer plastic one, problems go away. It seals it right up. We're not getting crossover. So, I mean, that's an example. And I'm not trying to beat up on Moen. Moen's great. They have good warranties and good products. But anytime you bring cold and hot together, you have the risk of some crossover. And the internal design of those fixtures has to prevent that. 604.3 talks about water distribution system design criteria. As I mentioned, if we're going to go and design a system to deliver water, what do we need? Well, at a minimum, this needs to be designed for peak demand. That means if we have so many fixtures, could they all be functioning at the same time? And if so, then what size pipe would be required in order to deliver? At a minimum, this says, well, you can't be any less than what the tables in this code have to say. And that's where we come to table 604.3. Have a look at table 604.3 with me. The water distribution system design criteria required capacity at fixture supply pipe outlets. Say that 10 times fast. May I point out that this table is going to give us a list of minimums. You might even pencil that into your book. Minimums. Minimum meaning this is at the lowest what we should be able to deliver with our piping system. The first column gives us fixture supply outlets served. So here's a whole list of fixtures and appliances that we're going to be delivering water to. The second column gives us the minimum flow rate in gallons per minute. Here's a simple example. Let's look down at private lavatory. If you have a private lavatory, 0.8 is the minimum amount that can be delivered. But connected with that also is the third column, where we have flow pressures. So we're delivering a certain gallon per minute flow rate at a minimum flow pressure of, say for that lav example, 0.8, it would have to have a flow pressure of 8 psi. Now there's a difference between static pressure and flow pressure. This doesn't mention static pressure, but static means it's holding still. When you have all the valves closed and the system is holding water, that's your static pressure. Yeah, a good one's 65 or so, right? 65 psi. But once that water starts flowing through an open valve, then we're going to have a flow pressure. And that's where we see what these are, right? Notice towards the bottom, we have some fixtures that require much higher flow pressures. For example, you have the water closet flushometer valve, 45 psi, and it has to have a 25 gallon per minute flow rate. Now let me point out, we're not going to let 25 gallons flow through the toilet when it flushes. But at the rate that it's being delivered if you let it go for a minute, it would equate to 25, right? And that's where we can gauge what this delivery is. Now, you and I are not going to go actually measure how many gallons per minute are happening, but this is design criteria. And our systems have to be able to deliver this, or the fixtures won't function. Let me specifically state, a flushometer will not flush if it doesn't have enough flow pressure and gallons per minute moving through it. It just won't go. We've talked about minimums in table 604.3. Go to table 604.4. Now we're looking at maximum flow rates and consumption for plumbing fixtures and fixture fittings. 2 columns on this one, right? We have the column on the left that says plumbing fixture or fixture fitting, and there's a smaller list here. And then on the right it says maximum flow rate or quantity. In this case, we're saying we're going to supply water and the fixtures are going to run, but we don't want to overdo it. As we talked about, water is precious, and therefore we should restrict that a bit and not allow too much to go through. That said, the shorter list here says lavatory private, you can have 2.2 gallons per minute at your sink at 60 psi. But when you get into public, and this becomes important for anyone who's doing commercial work and installing, public lavatory other than metering, 0.5 gallon per minute at 60 psi. That's like a quarter of the amount of water being delivered from a residential or private lavatory to a commercial. How do they do it? Well, once again, it's the aerator most of the time, and you can swap out aerators. You can put in an aerator that will restrict that to 0.5 gallons per minute. The other one there is metering lavatory. A meter is where you push down that handle and it stays on for a short period of time and then it turns off. They're the kind that drive us all crazy because when they're not set correctly, you push it and it shuts off immediately before you get a chance to wash your hands. Those are 0.25 gallon per metering cycle. Shower heads are limited to 2.5 gallons per minute at 80 psi. Sinks, 2.2 gallons per minute. Urinal, 1.0 gallon per flush. When we're looking at urinals and toilets, we're not talking about gallons per minute. We're talking about a flush cycle. And urinals are limited to 1.0. Now in commercial settings, when there's water conservation happening, I've seen and installed 0.5 gallon per flush cycle urinal flushometers. Personal opinion here, they don't wash the fixture. You kind of want to rinse that off pretty well when it's done. That's my opinion. Water closets, any toilet, be it tank or flushometer type, 1.6 gallon per flush cycle. This is where in code we are limited to how much water we can use per flush. Now a lot of toilets are going to 1.28 gallon per flush cycle. That's great, as long as they can get the job done and wash the bowl. But 1.6 is the max. Now 604.4 does give us a list of exceptions where you look at the fixture and say, you know, we probably need a little more water to get the job done. Exceptions including a blow down design water closets, the ones that used to use 3.5 gallons per flush. Vegetable sprays, probably going to use a little more water. Clinical sinks, they say, 4.5 gallons. Service sinks and emergency showers. These we may have higher volumes because we need it. Join me now on one more table. This is 604.5. It says minimum sizes for fixture water supply pipes. And this section says, well, you gotta meet this at least for your pipe sizes. When we get into sizing, depending on the load, we may have bigger pipes. But let's say to whatever fixture you're supplying, here's the smallest you can possibly go. The left column gives us a list of fixtures. The right column gives us a list of sizes. It's really simple, right? Bathtubs, 1/2 inch. Hose bibs, 1/2 inch. Lavatory, 3/8 of an inch. Toilet, 3/8 of an inch if it's a flush tank. If it's a flushometer, 1 inch. Urinal, 3/4 of an inch. So you can see depending on the fixture, we're going to have a minimum pipe size delivering water. Also in 604.5 it says the fixture supply pipe shall terminate not more than 30 inches from the point of connection to the fixture. We're talking about the supply tube. You can get 20-inch poly supply tubes. You can get braided supply tubes of various lengths. You can get 30-inch poly supply tubes, but any longer than that, and that's not allowed by code. 604.6 talks about variable street pressures. It says where street water main pressures fluctuate, and they can go up and down, the building water distribution system shall be designed for the minimum pressure available. So if you know you're going to have high pressures and lower pressures, but it's all within this safe range, well then let's design it for the low end, just in case we end up there a bit, so that our fixtures will still function. In situations where that water delivery may be inadequate, 604.7 talks about providing more. It says wherever water pressure from the street main or other source of supply is insufficient to provide flow pressures at fixture outlets as required in the tables that we've looked at, the water pressure booster system conforming to 606.5 shall be installed. So basically, you get a booster pump and you push it to a pressure that works at the fixtures. I've seen city pressures in some locations that are at 25 psi. That's worthless. Your fixtures just won't run. So there's a different design on those houses. Particularly an enormous storage tank with a booster pump that can then pull as much as necessary at the time and deliver at the pressure needed. So what happens if the pressure is too high? 604.8 goes over pressure reducing valves or regulators and states that where pressure is within the building exceeds 80 psi static pressure, we talked about static, then you would need a pressure reducing valve. So as a plumber, may I say, anytime and every time you install a system new, or if you're servicing and working on some system, you should check the pressure. You always should. You should always know, because look, if you install something and the pressure is above 80, what if it's 100? What if it's 120? And you don't check that, that could wear out your fixtures, it could kill your water heater, and they could blame you, right? They could be, what's wrong with you, plumber? You're leaking. Checking the pressure is a real protection for you and for the system. Not only that, but let's just talk about the money side. Anytime you check someone's pressure and it's too high, you should sell them a pressure reducing valve. And that should cost them something. And that should pay you something. That should be happening anytime that you go in to do any service, or if you're finished with the building, make sure to check it, because you're responsible for that. 604.9 goes over water hammer arresters. It says a water hammer arrestor shall be installed where quick closing valves are utilized. What is a quick closing valve? Any valve that has an electric solenoid that will just shut it off fast. Dishwashers, washing machines, things like that, that electricity controls the valve. They shut fast, the water's cruising through that pipe, it hits that valve like a wall, and it just bounces back and forth. The water hammer arrestor will take that impact and spare the pipe a lot of unnecessary pressure. Now they used to handle this by adding a T. They just put a leg with a cap and assume that the air chamber was going to compress as water would hammer inside of there. But the problem is that pipe fills with water and you lose your chamber and it's useless. So it has to be an actual device. There's a number of different mechanical water hammer arrestor devices. All of them use the same principle where there's a pressurized air chamber, and when the water pounds, it just compresses that air and alleviates that pressure surge inside of the pipe system. 604.10 goes over gridded and parallel water distribution system manifolds. Viega made the mana block, and there's a sizing table for this. Most of us who've been in plumbing long enough remember it was like the year 2000, and this was new and exciting, and everyone wanted to install this, and there were all these selling points for it. And then some time went by and we realized how horrible of an idea it was, because the valves don't work very well over time, but some people still like them, some people still install them. This is where we're dealing with different system designs, and there may be some advantages to this. From my service experience, I don't see very many. 604.10.2 says that the valves shall be identified. You can see in this that there's stickers, and the stickers tell you what those valves go to. So the idea was you could come to this and just be able to isolate a fixture by turning it off at the manifolds. What if plumber doesn't put the stickers on? That happens. Well, then you just shut the whole building off anyway, and this thing's useless. Or what if the valve is old and corroded from hard water and it won't turn? Well, you break your key and then you can't even turn them off. So you just shut down the whole building. You see where I'm going with this? I'm kind of glad that we don't install these a lot. Some people may have other opinions on this, but that's where I'm at with it. Access is required to be provided for these 604.10.3. And that is as far as we are going to go in Chapter 6 for this presentation. We've covered from 601 to 604. Join me next time and we will continue our discussion of International Plumbing Code Chapter 6, Water Supply and Distribution Systems. I'll see you then.